So, good evening, guys. So this is the first in-person lecture. How was the exam? Most of you received the good marks, right? And you might realize the importance of attendance. So the exam, also similar to the midterm exams, the final exam will be covering like all lectures, what I explained. You don't need actually extra materials. You don't need to look at anything else. All you need is just to study every single word I just explained to you, because I might ask you about alternatives similar to AMI or differential or whatever. But again, the exam for me is straightforward. Once you study the materials I explained here to you, you'll be fine. So did you notice anything strange in the midterm exam? Okay, you might didn't study something, right? But like again, did you find anything outside the slides or what I explained? Okay, so I do recommend from now till the final exam to study everything I just explained to you, because if you miss a slide or two, you might see a question in the final exam. Okay, so anyhow, let's continue. As I mentioned last time, I will do my best. First of all, I will do my best to record the lectures here for your reference. But again, sometimes it might be like technical issues or something like that. So don't rely on the recorded slides or whatever, because for example today I supposed to have better resolution than this, but again I forget a connection or a wire or whatever, a cable. So in this case, just attempt, write everything, and then you will be fine. But again, I will try my best to record, and I will post the recording after the class, hopefully. Yeah. So anyhow, the second assignment will be posted by Friday, right? You will take 1 week to submit it, so the due date will be following Friday. The third assignment, the second assignment will be similar to the first assignment. It will be like some problems related to module 3. Some of them you will be familiar with. Some of them you need to read in order to solve it, because again, you will be given the question and you will see also the solution, because all the problem will be from the back of chapter 7 from textbook. So you will be given as a question, and you will have also the solution. So you need it just to comprehend or like to understand, and they try to solve it using what you understood from it. You'll notice that also some of the problems I will see first, but some of the problems, for example, matched filter. I explained matched filter using a graphical method, right? But there is also a mathematical method. I will not explain it, right, because of the time limitation, but you might find some problems in the second assignment that will not be solved by graphical method. You must solve it using a mathematical method, okay? But you just need, again, this is not required for the final exam. This is just for your information, right? So you will understand that, because I consider the assignments just reading assignments or comprehensive assignment just to complete the understanding of the whole course, right? But again, if you found something not straightforward from lectures, this will not be included in the final exam, okay? So don't come and ask me again, similar to the midterm exam, when some of you asked me about the first assignment, is it included in the midterm exam or not? No. What will be included in the final exam or the midterm exam from all courses I teach what I just explained, okay? But the assignments are just kind of complementary material for to complete the understanding. The third assignment, you will be given, I think, 10 days or 2 weeks, because you will be given, it will be about the fourth module. You will be given 2 papers, and these 2 papers is related to the fourth module, and then you need to summarize these 2 papers and and write a report about these 2 papers. So that's why I will give you like 10 days or 2 weeks at least, at most. So in order to be able to finalize it, again, will be 2 easy papers, and also I will explain also the concept of them during the fourth assignment, or during the fourth module. Okay, so again, this course will be 5 modules. By Friday we'll finish the 3rd module, the 4th and 5th module. The first one it's a little bit short, so each module will take 1.5 weeks, or like 2 weeks at most each module, right? So anyhow, we will agree about how many questions per module you expect in the final exam, similar to what we did in the midterm exam, but like when the time get close. Okay, so let's start. Hopefully what I mentioned it just recorded, but anyhow, you are here. Okay, so today we'll be speaking about a symbol synchronization. After we discussed about, we are now in the transmitter side, right? So we derived, or what's the basis function you need actually to drive in order to find the orthogonality, or making the job easy at the receiver side in order to detect the symbols. And we did like matched filter, we spoke about everything. Now we need to take samples. Remember, we are working in digital domain, and typically you have the digital signal and then you transform it to analog in order to be travel it continuous. It's not analog, it's continuous. But again, as a receiver side, you're not dealing with the whole pulse. You need only to take one sample, okay? So the sample should be taken in the middle, like for example here. Hopefully you can see it. Like again, I'm sorry because I'm using the camera. Hopefully next time I will use, if I use like the direct presentation, you will not see the recording, which I think this might be important for you, the recording one. But anyhow, so suppose that we have the pulse itself, and then we have the matched filter, right? So for the matched filter, we agreed about the properties of matched filter, that the peak is the minimum in the middle of the pulse, right? So we have the twice of the pulse, right? So the original pulse was t, and then you have 2t, and the shape is symmetry. We agreed about everything about that, like last lecture before the midterm exam. So we need to take the pulse exactly as the receiver side at the middle of this matched filter, okay? Because once you receive the pulse, you do the matched filter, and then this is the output of matched filter. And again, you need to set up your clock, right? Your clock means that you take sample every time, right? This is called a clock, or the frequency, right? So you take sample and wait a period of t, and take another sample and wait another period of t, and take another sample, and so on. If you missed the first clock or the first sample, then you will be having issue in shifting, or issue in having samples in the middle of each pulse. So actually, I need to design a network or a circuit, a block diagram, whatever, that can take a sample exactly in the middle of the pulse. Why the middle of the pulse? First, I need actually, this is the benefit or simple synchronization. So like we missed to explain that. So simple synchronization ensure that the samples occurs at the right time, okay, within each symbol. And the benefit of that, in order to maximize the signal energy, remember the middle of the pulse is the maximum value, so I need to make sure that this is exactly in the middle. And also we need to minimize the intersymbol interference. If you remember in line coding, we have like overlapped sync functions, right? So, and we explain that I need to take the sample exactly in the middle in order to minimize the intersymbol interference, right? Because if you shift a little bit right or a little bit left, in this case, you have your pulse in addition to the adjacent pulses, okay? So you will have actually intersymbol interference. So if you actually can obtain a sample exactly in the middle of the pulse, in this case, you will minimize the intersymbol interference. And at the end of the day, after you do this, you will accurately detect the symbols, because if you reduce the intersymbol interference, all you need actually is to overcome the effect of the noise. But if you have the noise plus the intersymbol interference plus the distortion plus a lot of things, this will affect the accuracy of detecting the symbol. Okay, so how can, okay, we agreed about the benefits of having a perfect synchronization, but the question is how to design a circuit, or how can we obtain this kind of exact sample at the middle of the pulse? The answer is early lead gate synchronization, which is widely used. So let's think about the idea, because you need actually to understand this block diagram of early lead gate, which is like, it looks like very complicated, but once you understand the concept of it, you will find it very trivial. Okay, so let's do some kind of brainstorming about the idea, how to obtain the exact pulse in the middle. Okay, so this is a pulse again, and this is a matched filter. At the receiver side, we did the matched filter. We studied how to obtain actually this kind of shape or whatever, and you solved this one in the midterm exam. But anyway, so we will do a little bit trick, okay? Because we have here, okay, if I will, you will not hear my voice, so I must stay, unfortunately. Okay, I might use this mic. Okay, so I feel nothing different, right? Okay. Okay, so we can apply, actually we can use a little bit or a little trick. Okay, so I need actually to take a pulse here. This is the optimal one. And I know that the matched filter, whatever the input pulse was, I know the matched filter is symmetric, right? So to obtain exactly here in the middle of the pulse, what about if you take sample before, which is called early sample, and take another sample late, and compare between these two samples, right? If this middle distance between these two samples, or if you like subtract the amplitude of this one minus this one, and it was 0, in this case the middle distance between these two samples must be in the middle, right? And if you shift a little bit right, so for example, if you start from here, okay, and like consequently the late sample will be here. So in this case, this value will be bigger than this one. I don't know if I can write it here. Let's do that. Okay, so here, if I take a sample here, guys, I need to start my PowerPoint. Okay. So suppose that we take a sample here, and consequently this distance is fixed, right? So we will take another sample here to keep the distance, right? So in this case, if you subtract this one from that one, you will obtain a value, right? Greater than or smaller than 0. In this case, you know that you are not in the middle. So you might need to adapt yourself to a little bit doing a shift toward right or shift toward left. Okay? So by doing this concept, you take early sample and you take a late sample and take the absolute between them and you subtract them. Okay? So you have an indication if this value, the error or the difference, actually it's not an error, the difference between them are not equal to 0. In this case, I need to move right or left in order to make some kind of looping in order to obtain equivalent value. In this case, I will take the sample in the middle distance between these two samples. Okay, so actually the concept of early late sample, this is called early late gate, right? So that's why it's called early late gate. It comes from early sample and late sample. Okay, and we have a component which is like VCO, voltage control oscillator. We can apply this error or the difference between these two samples to as an input of VCO. VCO is a common component that when you apply a voltage to it, it can change the frequency. Correspondingly, it will change the time because there is a relation between the frequency and the time. So in this case, by VCO, we can actually make the pulse advances toward right or blade toward left. Okay, so we apply actually this error as an input of VCO, and the input of VCO will be changed toward right or left if we have a value, but if we have 0, the VCO output will not change, right? So in this case, I reach it to the synchronization state. if you look at this block diagram, you will see exactly what I just explained. So as you can see here, this is the received signal, and this is the matched filter. Remember when we upload the block diagram of matched filter, you can represent it by multiplier and integrator, or you can represent it by the psi function, or as we explained last lecture. So you need actually to understand and memorize this kind of block diagram. Okay, so this is a matched filter, but this is using advanced, right? So the late or the early advanced, like the early pulse, and here this is for delayed one or late pulse. Okay, so this is matched filter in order to obtain this one here, and the lower branch in order to obtain the late sample. Okay, and here after you did that, you take samples. These samples represent the early one, and you take a sample here. This represents the delayed one or the late one. Okay, and you use the magnitude or absolute here, similar to the previous equation here. I need to obtain the difference, so I take the absolute value, because in some matched filter, as we studied last lecture, you might have a negative values, right? So in this case, you take the amplitude, and then you take subtract between them, or you take the difference between them. So as you can see here, this is the magnitude of late branch, and this is the magnitude of early branch. You find the difference between them, and you input them to loop filter in order to make sure that the bandwidth is the desired bandwidth, and then you apply it to the voltage control oscillator. By having a value here, this will change the duration, or the time of each sample. Like it can be little bit changing toward right or left according to the input here of VCO, and then wave generator, or like waveform generator, because I need to generate the waveform again in order to go with the same loop. So it's very trivial. It just based on a basic concept that I take early sample and I subtract it from a late sample, and based on the difference between them, I can adapt these samples using a VCO, and then I can do this loop until I obtain a zero here, or the error here should be zero. In this case, it will no update here at the output of VCO, and then I will reach to the synchronization status. Okay, so this is early lately, and the last part of this module, if you remember when we explained the optimal receiver. So this is just a recap. Okay, so here this is from like 2-3 lectures ago. So we discussed that the optimal receiver is, we have two types of the receivers. The receiver structures contain two types, like the demodulator, which we studied the correlator or matched filter, and the other thing is the detector. The detector, after you receive the signal, the desired signal, you need to understand if this signal was 0 or 1. You detect here R, right? You detect R, just a voltage, a value, but you don't know, you didn't need actually to map or demap this value, this complex value, in order to, or demap it to the original symbol you transmitted. This is the purpose of detector. We discussed the demodulator part before the midterm exam, and the rest of this module we will be discussing the detector. Okay, so in detector we need to decide the received signal R, right? which symbol you was transmitting out of M signals. Okay, so this is a main part actually of this today's lecture. So as we mentioned here, for the transmitted signal, I have I have like here. Okay, so I have here, this is the transmitted signal, but unfortunately I have some noise from the channel, which is N. It follows, as we mentioned, it follows a Gaussian distribution, and at the end of the day I will receive R, which is the transmitted symbol plus the noise. Okay, so this is actually the definition of these symbols or these parameters, and you can see that the transmitted symbol Sm is one of M possible transmitted symbols. So like if we use a QAM or 4 QAM, so we will use one of 4 symbols to be transmitted. If we use a binary BSK, we will use like only 2 transmitted symbols, and so on. Okay, and the noise here, this is important thing, the noise here has a spherical symmetry shape around the original symbol. What this means? Actually, we will spend a lot of time here. This is very important, guys, to understand, because we will do some kind of derivation based on the understanding of this sentence, right? So I'm claiming here that the noise will will behave as a spherical behavior around the original symbol. Okay, so let's explain this in more details. But before we go with, keep in mind that the received signal is the original signal, which is a deterministic one, a plus noise. Noise is a random, right? And follows a Gaussian distribution. Okay, so if there is no noise, in this case, I will transmit SM, I will receive SM. But unfortunately, there is a noise, and the noise is random, right? So I will see that these values of SM will be added to some random noise which I do not know. Okay, so to understand this, because again, the job for this part as an optimal decoder or optimal detector is to detect the original SM outside or out of this noise. So we need actually, if you decide SM correctly or receive it correctly, this is great, your accuracy is good. But sometimes you decoded it or you detected it wrongly. And in this case, we need to calculate what is called a probability of error. Okay? So keep in mind this equation, R, the received signal, equals the transmitted symbol plus noise. Okay, so recall the properties of noise we just explained as the second module. So we have the noise is Gaussian, right? So the BDF of the Gaussian is given from here 1 over 2 pi square root of 2 pi sigma square exponential x, or this is the variable x, the random variable, minus mu. Mu is the mean, and divided by a square or 2 sigma square, which is the variance. Okay, and this was the plot of the BDF, right? This we studied this in more details in the second module. But here I just need to recall something. Remember, the value of noise, the value of variance is directly affects the power of noise, right? Okay, and like a raised question, do you prefer high value of noise or lower value of noise? High value of variance or lower value of variance. Okay, from this figure, as we can see here, as you increase this one, like the red one here, like as you can see, I'm not sure you can see it, but anyway. So here, this is variance of 3. The red one is, the variance is 3. I wrote it twice. Okay. So the variance is 3, the red one. And if you reduce the variance to be 2 in the orange curve, I finished writing and still like didn't show up. But anyway, so the variance of orange one is 2, the variance of green one is 1, the variance of blue one is 0.5. As you can see, as we reduce the variance, it become thin and tall, right? Until you use 0 variance. 0 variance means that this is like a infinite or infinite line, right, in the middle, which means that this is deterministic. Okay, there is no distribution, because recall the concept of BDF. BDF means the probability density function. You need to see the distribution of this random variable over x-axis. Okay, so once I have here like a straight line with 0 variance, in this case I have a deterministic value. I have only the value, I have one value at this time, or at this value x equals 0. I don't have any value. I don't expect that this value will come here, or like before x or after x. Okay, so I need actually to, like, for like less values of noise, you need actually to reduce the values. Anyhow, this was like recalling from the second module, and this was like 2D. Okay, so let's see the 3D of this Gaussian shape. As you can see here, like it's, oh, you can see it. It's not okay, because the response of this camera is low, is a little bit low. So I can actually do here, this is a PC, for example. Okay, and I can show it to you here. So as you can see here, this is like, if you look at the Gaussian distribution from the top, you can see it like a circle, right? So, and if you shrink the noise or the variance, the circle will become a smaller one, okay? So keep this concept in your mind, and let's go to the next slide. Was here. Okay, so this is, suppose that I have a numerical example. I have, remember that I have R equals Sm plus noise. We are waiting for the noise. Okay, it will come. Okay, I didn't go. Okay, so here, suppose that we have this binary sequence for QBSK. So I have 0, 0, 0, 1, 1, 0. I have like this bit of sequence, and I have the transmitted code word is -1, negative 1j, negative 1, positive 1j. This is actually the transmitted code word from QBSK. Okay, so you don't need actually to memorize this code word, but like I need just to give you an example in order to understand what these kind of plots. This is called a scatter plot. Okay, so I have two components here, real and imaginary, and this real represents like in phase component, and the imaginary represents the quadrature component. So I can plot these four symbols as a points here, right? So this point, for example, this point is one positive 1, negative 1, right? So in this, because negative 1 here, so the coordinates of this one is a positive 1, negative 1, I'm sorry, negative 1 on x-axis and positive 1 on y-axis, negative 1, positive 1, which represents 0, 1, and so on. This one represents 1 on x-axis or in phase component, and represent also 1, positive 1j on y component or quadrature component. So I can plot from here what is called a scatter plot. If you are working in digital communication, you will hear this concept is scatter plot, scatter plot. So actually we plot scatter plot based on the in-phase component, in-phase and the quadrature components, or the real and imaginary, okay? So each QAM, you have a corresponding imaginary representation for it. If you have 8 BSK or 4 QAM or whatever, you will see a different representation for this code. Okay, so we plot the scatter plot, and again, this is the ideal one. So if we notice here, if we don't have a noise, so in this case, the received signal will come exactly at this x, whatever, like suppose that I transmitted S1. This is S1, this is S2, this is S3, this is S4. So suppose that I transmitted here S1. So if I transmitted S1 here without any noise, I will receive here this value exactly, because I don't have noise. But unfortunately I have noise. And keep in mind, the noise is Gaussian distribution, and we looked at the 3D shape, we found it was a circle. Okay, so in this case, actually, we will have this one here. So this is like animated QBSK. As you can see here, this is the original symbols, like the ideal symbols, like the X1, the ideal ones. And once you transmit the symbol, this symbol here, because we have R equals SM, the symbol plus the noise. And if you remember the experiment we did using a MATLAB, we generated a random variable and we obtained a different values of different values. It will follow just the same distribution, but the values itself will be different. In this case, as you can see here, I might receive, instead of receiving it at this point exactly, I might receive it here. I might receive it the second symbol. I might receive it here. I might receive it here. Like you will see something around the original symbol, right? And eventually, after you transmit a lot of symbols, like thousands of symbols, you will see that the original one here in the middle, and you will see almost a circle around the original one. Okay, that's why the biggest statement that the noise will cause a spherical symmetric spherical shape around the original symbol. Okay, so but it comes here, this one comes first, the second one comes second, and so on. At the end of the day, this will represent the circle. If you remember the circle of Gaussian itself, right? Because this noise is added to the original symbol, so it can be one of the values of this circle if you look at it from top. Okay, so and if you increase If you increase the number of symbols, actually, like you transmit 10,000, like 10 power 6 symbols, you will see this exactly a circle. Okay? So, well, this is great. Again, this is the original symbol, which is the x-axis, and the blue dots represent the noisy received signal. Okay, so I received this value. Suppose that I received only this value. Okay, so what is the main job of the receiver? The receiver is to detect this symbol. So from here, as you can see here, once you receive this symbol inside this area, you will say that this most likely was this one, right? Suppose that this is S1, this is S2, this is S3, this is S4. So if you receive this symbol, you will see that, you will say that it was S1. If you receive the symbol here, for example, if you can see, so you will say that, you will decide that this symbol was S2, and so on. Like if you receive this symbol is not matched exactly with the original one. You don't have any value for that. Like this is the original symbols. Okay, so if you plot this one, it will come the cross here, like the red cross here, right? But with the effect of noise, you receive these values here around the original one. Okay, so if you receive this one here, you will decide it was this one. But again, the question is, why, when you receive this point, you decided that this one is most likely S4, for example? Because actually in your mind, you measured the distance between this symbol and the original one here. You measured this distance, you measured that distance, you measured that distance from the received signal to one of the symbols, and then you decided that this symbol very close to that one, so I will decide this is the fourth symbol, right? So similar to anything logically, if we have argument between us, so is this pen belongs to me or to anyone of you? So you will see the distance. If you found this pen very close to me, so this is makes sense, most likely it's mine, right? If it's like very close to you, most likely it's yours, right? So this is the main concept. So, but how can we proceed this at the receiver side? We do what is called a boundary zones. We take the distance between these two received signal or the original ideal symbols and take the difference or the half of the distance, like I divide these distances. So in this case, if I received any symbol lies on this boundary zones, this is called a boundary zones or thresholds between these two symbols. If I receive any symbol here in this area, I will decide it should be S4. If I receive any symbol inside this area, I will decide this symbol belongs to S4, right? Okay, this makes sense. So now we have a concept of what is called a boundary zones. Okay, the main idea of today's lecture, how to calculate the boundary zones. Okay, but this is not all thing or all what I need actually before I drive the boundary zone. So what about if I, for the same value here, the previous one was a QBSK. What about if I change the signal to noise ratio, right? Because again, the signal to noise ratio is the ratio between the signal power divided by noise power. Okay, so the signal power is fixed, but the noise power is a function of the variance. So originally, when you try to change the signal to noise ratio, we change the variance. Remember, if we return it back to here, when we change the variance, we shrink or we extend the circle around the original one, right? So if you look at here, signal to noise ratio is 10 decibel. 10 decibel means that like the previous one here, it was where that like oh yes, the previous one. The previous one here was plotted using a 5 decibel. Okay, so here this is a 5 decibel. This is the previous plot, right? 5 decibel here. So if I reduce the signal to noise ratio, this means that I increase the noise, which means that I increase the variance of noise. In this case, I will increase the circle of the noise, or the received signal will come around the original signal, or the ideal symbol. In this case, everything will mix up. Will mix, like you will be mixed between this transmitted symbol and that transmitted symbol. And if you increase the signal to noise ratio, this means that you reduce the variance of the noise, or Gaussian distribution. In this case, you will shrink because you reduce the variance. It will become very shrinking. So actually, the signal can be distinguished easily. So in this case, the receiver side, if you take this region to decide which symbol belongs to S4, it will be easy compared to the first one. And if you increase signal to noise ratio more, which means that you reduce the variance of noise, in this case, it become more easier. Like again, it like yields to, or like goes to the original or the ideal one. Okay, so this is for 4 QAM, or I'm sorry, for 4 BSK, which is like QBSK. But what about if I increased also the symbols? Instead of 4 symbols, I have 8 symbols. So as you can see here, like here was a good shape, and I can easily decode or decide which one belongs to the original one here easily at 5 decibel. But look at here, when you increase the number of symbols at 5 decibel, even by your eyes, you cannot distinguish between what was transmitted. So this is the original ones, right? But this is good at 20 decibel. But for 10 decibel or 5 decibel, as you increase the number of symbols, it will become very hard actually to detect the original symbol. You can detect, but with expected higher value of error. Okay? Why I do all that? I just need you to understand the boundary zones is a mathematical formulation. We will do it now, but it cannot guarantee that you will receive the signal in a good way. Still, there is a kind of error. That error depends on the number of symbols you use and the operating signal to noise ratio you are working on. Okay, so if you can, if you would like, and there is another thing is the equal problem. Okay, so look at here. This is the 4 QAM, or I'm sorry, 4 BSK. Actually, QBSK is equivalent to 4 QAM, by the way. It's just a special case. Okay, we use usually QAM in most of wireless communication. That's why I say usually QAM. But anyway, QBSK, I have 4 symbols. This is exactly the same figure as before, but I colored the 4 symbols in order to see another concept now. Okay, so look at the green dots here, as we can see here. So the green dots here, this is the threshold between them. If you look at, if you can notice this one, like I'm not sure if you can notice this one or not. See here, what's the color of this symbol?
Green.
Green, yes, exactly. So, but this green symbol, it originally sent by S1. But according to the boundary zone here, this one comes in the region of S2, right? So in this case, if I receive this symbol, the green point here, I will decide it was S2, which is error, right? That's why in the next lecture, we will derive the expression of probability of error, right? But anyway, so here, I know that because in the previous figure, if you look at the previous figure, you might see this value or that value, and because of its similar color, you might decide this is okay, this is S3 or whatever, and you are sure that this is S3. But using the colored one here, as you can see, this one will be detected as S2, however, it's S1. And also look at the yellow one here, right? The yellow one here will be detected as S1, however, it was S2. And look at this one here. There's two symbols here, right? These two yellows will be detected as a blue symbol or S3. And the same thing here, look at this one here. This is like very away from the original one. So this one, it's a blue one, will be detected as a black symbol, which is S4, however it was S3. That's why there is what is called a probability of error. The majority of symbols will be correctly detected. However, there is some error, depends on, look at the circle here. Do you expect that if we increase the signal to noise ratio, in this case we'll shrink this circle? In this case, we will reduce the amount of outliers here. We will reduce the amount of the symbol will be detected in error. Okay? So this was actually equal probable. What's the meaning of equal probable? Equal probable that I will send the whole symbols the same probability. So I have a source that generate 4 symbols as an example. This source will send the signal like it generates the symbol 1, the frequency of the signal will be similar to the frequency or the number of sending of S2 the same as S3, the same as S4. This is called equal probable. But what about if I play with the probability of sending this symbol? For example, suppose that I have 4 symbols similar to this one, 4 symbols which is like QM or QBSK, but I'm sending S1 which is in green 70%. So like I have a source, like for example, similar to the English letters, right? So you use A, maybe B or E more frequent than Z or Q, right? In this case, you have a different distribution, you have a different probability, okay? So if you have equal probable, it will give you the same thing as here, and the boundary zone, you should expect that it's exactly in the middle between these 2 symbols, okay? Because it's equal probable. But now, I have unequal probable. I have a source that generates S1 70% more frequent than S2, S3, S4. So if you transmit thousands of symbols, you expect that 70% of them will be S1. In this case, it's like unfair to make the threshold or boundary zone in the middle of these 2 symbols. It's unfair, right? Because you need to move, you need to give the higher probable symbol a wider area, right? A wide, instead of, because here, look at this zone or this area for S1. This is square, right? And for S2, this is square. This square is similar to this square. And this square is similar to this square. So this is the boundary zone here. Okay, so once I receive any symbol or receive symbol here inside this area, I will decide this belongs to S1 or S2. But again, since I have not equal probable, it's unfair to use equal spaces or equal zones for all symbols. This most of frequency one or like most probable one, so we need to enlarge the zone for it. Okay, so you need actually to move this line a little bit wider here toward here, and this line a little bit wider. As you can see here, these ones here, a lot of green symbols here, which is expected, right? And the same thing here, a lot of greens here compared to this one. So see here from the green one, how many outliers outside the green area? Just one or two, right? So, but here, I have two here, went to the black zone, and I have a lot here, a lot of green outliers here, went to the yellow zone, okay? So, all this kind of simulation or graphical illustration, in order to understand that, the noise will make the distribution of the noise will play an important role in order to detect the symbol correctly, or in order to set up a threshold or the boundary zone between between the transmitted symbols. Okay, so now, and based on the probability as well, based on the number of symbols, the value of signal to noise ratio, and also is it equal, probable or not. So the question now, how can we calculate the optimal threshold? As we can see here, we discussed there is a threshold, we discussed it, but how can we calculate it, right? So now, in the last few minutes, the last 15 minutes actually, let's calculate the threshold. Okay, so here, this revision is important, guys, okay? So this revision, step by step, is very easy, but you should know. Okay, so we need here to drive the optimal threshold, okay? So the optimal threshold, as you can see here, this is the distribution of the first symbol. Suppose that this is only for two symbols, and we will be discussing only two symbols. Suppose that this is the first symbol I have, and its amplitude is A, and here this is another symbol here, negative A, and this is the threshold I need to set up. It's gamma, right? So gamma is unknown. I need to drive it. I need to find the rule for gamma. Okay? So before I start, if it's equal probable, in this case, this threshold must be at 0, right? The middle distance. If it's unequal probable, it might shift right or left. I need to give like wider area for the higher probable one. Okay? So why I plotted this Gaussian distribution? Because again, the received signal, remember, received signal equals a deterministic term, which is S1 or S2, a plus noise. And the noise is given from the Gaussian distribution. So the received signal actually will be a Gaussian distribution shifted by A or negative A, if we transmit A or negative A. Okay? So this Gaussian distribution, or this is a PDF of Gaussian distribution, I just recalled at the beginning of today's lecture. Okay, so this is actually conditional distributions. This is the blue one is a distribution F for received signal when you transmit S1, given S1. And the blue one here, or the yellow one here, represents the distribution of received signal given that you transmitted S2. Okay? So basically, logically, when the error comes, or where you need to set up your threshold, which is minimizing the error, right? Okay, so here, for example, you decide the received signal to be greater than the threshold, then you will decide S1 here. For example, this is the threshold. If the received signal is greater than the threshold in this area, in this case you will decide S1. But if the received signal comes here in this area, in this zone, then you will decide like R smaller than threshold gamma, then you will decide S2. Logic, right? It's logic, right? So if I received the signal here, this is just a transformation, guys, of this boundary zone, right? Again, if you look at the distribution from the top, you will find it circle. Okay, so we return it back here to the 2D one, right? But if you look at from the top here, you will find it circle. Okay, so this is the meaning. I have only 2 symbols, but this is example for 4 symbols, but the division for only 2 symbols. So I have, suppose that I have these 2 symbols. So once you receive the signal here greater than this threshold, then you decided S1. Once you receive it smaller than the threshold here, you will decide it S2. This is what I did here. Okay, this is what I did here. R greater than gamma, or the threshold, I will decide S1. Smaller than gamma, I will decide S2. Okay, so I need to transform these 2 probability equations. This is what is called a MAP, or maximum a posterior probability, or decision rule. Okay, so to replace this one, like here, R greater than the gamma, or R smaller than gamma. Okay, so what is R? From the probability distribution, it's just the BDF. Remember the BDF of Gaussian distribution, right? So if I ask you about this proof, you will find the Gaussian distribution BDF in your formula sheet, right? So this came from Gaussian distribution. Remember this, what is the shape, what is the distribution of this? It's Gaussian distribution, right? So this Gaussian distribution, you replace here R greater than gamma, R smaller than gamma. So you can say that when you have here R given S1 times the probability of B1, right? Because I need to see, or I need to include actually the probability of it, like if it's equal or unequal. So this is the conditional distribution. Are given given S1 times the probability of B1 greater than the probability of R given S2 times the probability of B2. This, in this case, in this scenario, look at only this one here, this inequality. In this case, which symbol you will decide? S1. If the probability times the probability of S1 greater than the probability, like for example, I have a probability of the first symbol is, after you did some kind of calculation, you found that 60% belongs to S1 and 40% belongs to S2. So in this case, you will decide this belongs to S1, right? So this is the translation of it. I have a probability of S1 greater than S2. In this case, I will decide S1, right? And the same thing here, if you look at this one, probability of R given S2 was greater than probability of R given S1. In this case, I will decide S2, right? Okay, so this is the meaning of this kind of inequality. All I need is just blindly replace the probability here, the conditional probability, by this one here, okay? So in this case, I have the conditional probability, the Gaussian distribution, the representation for Gaussian distribution 1 over square root of 2 pi sigma square exponential R minus S1 here, or SI here is SI here. If you use S1, you will replace S1 by A. If you use S2, you will replace S2 by negative A. In this case, I will replace
this value exactly with this value. Okay, I will obtain 1 here, and remember there is 1 over square root of 2 by sigma square, but this term will go with the second term here, or the after the like on the right hand of this kind of inequality. Can you see here? Most of you, can you see here, right?
Yeah.
Okay. So I will plug in only this one here, and I will plug this one here, right? And remember, this is a probability of the first symbol, and this is probability of the second symbol. Okay, and 1 over square root of 2 by sigma square supposed to be here. The same amount supposed to be here. Okay? This is 1 over square root by sigma, sorry, 2 by sigma square is very slow. And here also 1 over square root of 2 by sigma square. This one will go with this one. Okay? So I have only exponential. Again, I'm looking for the threshold, which is R. Okay? So you need you need actually to take the natural logarithm for this equation. Okay, by taking natural logarithm for this equation, you obtain this value. Just you are using a systematic way, and then you need to bring them to one side. I'm looking for R, right? So you will add this one here. You will put that one here. Remember the natural logarithm or the len properties when you add them, or like you have a difference or subtraction between them, it can be transformed as a division. Okay, so in this case you will solve for R, and then you obtain finally R equals or greater than or smaller than sigma squared divided by 2a len, the first probability divided by the second probability. Again, if you look at here, if the received signal greater than this threshold, you will decide it R1 or S1. If this the received signal is smaller than this threshold, then you will decide it S2. So again, it looks complicated. However, it just you set up these two curves. This shifted at A, this shifted at negative A. You replace with this one here. If you use S1, you will use here A. Guys, please. Okay, and you just plug in these values and you try to solve for R. It's just a basic mathematics, and then finally you obtain this rule, and then return back to our previous or the main question. What about if it was equal probable? When you have equal probable, so this probability equals that probability. In this case, len 1 equals 0, and then the threshold is 0. Return back here. This makes sense. Oh, makes sense here, right? If I change it, like for example, if I asked you in the exam, for example, I give you here this one is 0 and that one is A. What is the difference? You will follow the same steps, but when you like suppose that this is 0, not negative A, and this is A or whatever. Okay, so instead of replacing, because this one is S1, which is here, I will replace A by A. It's okay. But here I will replace negative A for S2 by 0, right? So whatever the value here, the values here, all you need is just when you are speaking about S2, you plug this value, this mean. When you are speaking about S1, you plug this value, and you follow the same methodology. You take this amount, like you cancel this one from here, cancel that one from here, you take the natural logarithm to obtain this one, you solve for R, and then you obtain the formula for the threshold. Okay, but again, if it's equal probable, then in this case, this is like straightforward, easy. And you might try at home that you solve the same example, but with the second symbol centered at 0 and the first symbol centered at A. Okay? In this case, the threshold for equal probable will be A over 2, right? If we replace negative A by 0, and for example here, what is negative A, what is positive A? It's a polar, right? It's a polar representation in line coding. So 0 will be represented by negative A, and 1 will be represented by positive A. Okay, suppose that we have on-off, like we have 0 represented by 0 and 1 represented by A. In this case, this figure will be shifted at 0 here and A. And for equal probable, the threshold is supposed to be A over 2, not 0, because I replaced this one by 0. So this 0 and this is A. The middle distance will be A over 2. Okay, so you can do it at home as an exercise. You just replace, and at the end of the day, you need actually to find that at equal probable, you will find that this threshold at equal probable will give you A over 2. Okay, so this is a final thing, is a numerical example after you drive, because I might change the values of negative A and A, and then you drive the rule, and after you drive the rule, I can provide you with some numbers in order to calculate this equation. Okay, so recalling the rule, I just drive here. The threshold is, this is the threshold, sigma square over 2A ln P1 divided by P2. This is a probability. Okay, so in this case, so suppose that I have A equals 2, sigma square equals 0.25, the probability, the first probability 0.7, the second probability 0.3. Find the optimal threshold. Okay, I just apply the rule. I will just apply the rule, and then I will obtain the threshold instead of 0, because for equal probable, if it's 0.5 and this is 0.5, the threshold will be 0. But here, this is not equal probable. I found that it's a little bit shifted, right? So the decision now, when you are greater than the threshold, which is this one, then we will decide it was S1. When it's smaller than this threshold, we will decide it was S2 or negative A. Yeah, your question.
So will you be giving us the formula for the threshold, or do we have to grab it from the?
You have to drive it based on the like what is here. So I will not include. I will include only, like if I asked you, I will include only 2 symbols. Okay, so based on these values, you need to follow the same methodology blindly. Just like you replace, but again, if I asked you, I will give you this formula and the formula sheet, okay? But you will plug this value here to here, because this is a mean. So you will plug this one here, whatever this value. Here, as an example, it was negative 8. But if I provided you with 0, or negative x, or like negative square root of e, whatever, you will plug this value to be here, you will plug this value to be here, and that's it. You take the natural logarithm, you solve for r, and that's it. Once you obtain the rule, if I extend the problem and I give you some numbers, so you just plug in these numbers to the given rule, and that's it. If not, it's okay.
And will it always be Gaussian distribution, or?
Gaussian distribution. Because this module is called a transmission, like if you look at, return back to the name of this module is the transmission over additive white Gaussian noise, right?
Yeah.
Through additive white Gaussian noise. So it's only Gaussian.
Thank you.
Yeah.
I know that we only studied the problem of 2, 6 node, but I'm curious that if we extend not only 2, but also node, then this process is not efficient.
This procedure, you will follow the same procedure, but like with like you will study this symbol with the first adjacent one, and you will study the second symbol with the second adjacent. We will see the problem of 4 symbols in probability of error, right? So like keep your question till the coming lecture, okay? Because you will see more than 2 symbols. You will also follow the same thing, but I will not ask you about that. 4.
I ask a question about
Yeah.
the slide 27.
Okay.
So I'm not sure the purpose of this 09